Hello everyone, welcome to this video. In this video, we'll be starting with permutation groups. So let us first understand what is a permutation group. So it is basically a group, and the group elements in this case, they are functions which we usually call as permutations, right? They are defined from some set A to the same set, right? These permutations, they are also functions. So these functions are defined from the set A to the set A only, and so these are the elements of the group that form the group, and the operation that governs all the functions here is function composition. So the set of all permutations together with a function composition is known as a permutation group. So starting with the history of these groups, in the early mid 19th century, the group of permutations were the only groups which were investigated by mathematicians. So at the mid of 19th century, only the information about permutation groups was available, and mathematicians were working only on these kind of groups. So later on, different kinds of other groups came into existence, right? So, moreover, although the group of permutations of any non-empty set A exist, so that means to say that we have a set A. From the set A to the set A, we may define any number of permutations. The set could have infinite number of elements. The set could have elements apart from numbers. It could have some object or anything. Permutation means different combination of such objects, so that forms different permutations of different elements of the group. So although we may have permutations of any non-empty set A, right, but in our subject here, in group theory here, we'll be just focusing on the case where the set A is finite. So that means the case where it contains finite number of elements within it, right? Moreover, we take the set A to be this set 1, 2, 3 up to n. So we have defined what our set A could be. So it is of this form. Using this particular case of A, we'll be performing the calculations in this course for the group theory, right? So we take A to be the set consisting of all the natural numbers starting from 1 to n, right, where n is some positive integer. So the next question that arises is how we may define a permutation. For that, let us define a permutation which we denote by the symbol alpha here, right? It could be any Greek symbol. So right now I am saying our permutation is defined by alpha, and the set that we are taking over here is the set of all the numbers starting from 1 to 4. So it contains 1, 2, 3 and 4, right? 4 numbers. So here the permutation, it is a function, right? So this alpha is a function which is defined from the set 1, 2, 3, 4 to the set 1, 2, 3, 4. So it will take all the numbers from here and map it to here. And moreover, you should notice, you should remember this thing, that whenever we define a permutation, that permutation is both 1, 1 as well as onto. So that means we can define the inverse of this permutation, right? So keeping this in mind, we'll because all the elements would be mapped to all the elements backwards, so we say alpha of 1 is 2. So this is the definition that we are defining the permutation. It could be different for different sets, and there are several ways to define such permutations. So we have alpha of 1 is equal to 2, we have alpha of 2 is equal to 3, alpha of 3 is equal to 1, alpha of 4 is equal to 4. So this is how they have defined in this particular case. So we may have different cases also. We will be looking at more examples later on. So let us first try to understand this one. So this is defining each of the element under this permutation alpha. Now there is a more convenient way to represent this correspondent in terms of array, right? We are very comfortable using matrices. So what we do, we write this permutation alpha in terms of an array, where we write the input elements into the first row, right? So they are 1, 2, 3 and 4. Then corresponding to the element 1, we have, so alpha of 1 is equal to 2. So we have 2 written just below it, right? So for alpha is equal to 1, for the element 1 we have alpha of 1 as equal to 2, which is written just like this. For the next element 2 we have alpha of 2 is 3. For the next element 2 we have alpha of 2 is equal to 3, right? This is what we have defined here. For 3, alpha of 3 is equal to 1. For 3, alpha of 3 is equal to 1. And for 4, right, alpha of 4 is equal to 4. So this is how we define the permutation and write it in a array form. So here each of alpha j is placed directly below j for each j, right? So once you are clear with this array notation, let us see one more example here. So the example, in this example we are taking the set which contains the numbers 1, 2, 3, 4, 5 and 6. So here we are defining the permutation by the symbol beta. So the permutation beta of A is defined like this. So we have beta of 1 as 5, beta of 2 as 3, beta of 3 as 1, beta of 4 as 6, beta of 5 as 2 and beta of 6 as 4. These could be different for different permutations. In our case this is given to us. So this thing is given to us, right? So now we are interested to write it in array form. So what we have to do, we first of all have to write all the elements as the first row here like this, and the second row would consist of beta of 1, beta of 2, beta of 3, beta of 4, beta of 5 and beta of 6. So we just have to write all these values here. Beta of 1 is 5, so we'll be writing 5 here. Beta of 2 is 3, so we'll be writing 3 here. Beta of 3 is 1, so we'll be writing 1 here. Then beta of 4 is 6, we will be writing 6 here. Beta of 5 is 2, so we'll be writing 2 here, and beta of 6 is 4, so we'll be writing 4 here. So this is the array notation of some given permutation. So